Harvard Center for Geographic Analysis, and this is our first chance to meet the people in the CyberGIS community, and we're excited about it, and we really hope to know more about how an organization like ours can make use of and collaborate with the ideas that Shawan had about creating interfaces and creating processes that utilize these cyber infrastructure underneath for all kinds of great things. My work is on China's historical GIS, and I built a temporal gazetteer for it. So I've done a little bit of research on that is about spatiotemporal modeling, and we organized at AAG last year in Seattle some sessions on that topic, and then this year at New York we did one on working digitally with historic maps, and all of those presentations and our research bibliography about temporal gazetteers and spatiotemporal issues is online here. And at our center, we're a service center. We're not really a research operation at Harvard. Our mission is to support faculty and students in their teaching and research. And one of the ways that we did that was to build this world map interface. And this is basically an open source, built on GeoNode, OpenGeoStack, collaborative tool for sharing geo information. And one of the problems we have is how to load historical data, how to use timestamp data, and then how to query it or how to discover things and model them as they change over time. We didn't really know how to do this. We didn't have too many big ideas. And then suddenly we found in the center right next to us in Middle Eastern Studies, Todd Mostak was working on it. So now Todd's going to tell you how it works.
Hi, everyone. I'm not a GIS person by training. I actually work as a research fellow at the Harvard Kennedy School and doing research on Egypt particularly. But in my research, I came up with so many problems of handling big geospatial data. Particularly, I work with Twitter data sets, and once the data set started getting the tens of millions or hundreds of millions of tweets, it became a problem to handle all of that. So first off, there's the inadequacy of conventional desktop GIS for big data sets. So here comes the opportunity for the GPU, which is massively parallel. And if you program it right, it can assist some, but not all, of course. It can speed up a lot of processes. So this is, so I programmed the back end. I call it GEOPS. It's a column store database programmed in C++ and CUDA, which is the NVIDIA GPU programming language. It delivers real-time heat maps of a data set. Here, this data set has 100 million tweets. We're moving to real-time streaming for the upcoming elections, so that should be in the billions. Anybody can come onto this website and make heat maps and point maps, choropleths. Okay, so like I said, it's a column store, in-memory database. Text is stored as products. I came up with a system of storing text as products of prime numbers on the GPU. It basically allows for compression while also getting fast lookups. You don't have to build an index, so you can stream data onto the GPU. So as soon as somebody tweets, you can be, generating a heat map of that. Tests for spatial intersection are not performed with like traditional methods such as R-trees. I came up with a technique to rasterize vectors. Like it takes in a shapefile, it rasterizes it, it looks it up, and you can do basically almost a billion on one gamer GPU, 1 billion lookups a second, as opposed to like 1,000 in PostGIS. So we're getting almost 1 million times speedups. On the fly generation of point maps. It's fast enough where you can actually make animations about 1/20th of a second to make a heat map. Scales linearly with additional GPUs. We use an Amazon instance right now with 2 GPUs. We're getting a custom box with 4. I know it's nothing compared to what you guys have here, but it works. And it's also a WMST server. So any client, our world map is built on open layers, can interact with it. So I said I stored words as primes. I'll explain it more later. It's really not that complex. Basically, starting with the most frequent word in the corpus, say on Twitter, this is actually how it works. So I is the most frequent word. It gets the lowest prime, 3. We don't use 2 there's some reasons that make it faster to not use 2, an even number. So basically, you can take any text message and convert it to its primes. 2 is the 6th most frequent word. It has a prime 17. You multiply them together, you get this number, you store it. It's less than 2 bytes. And then you can check if any word is in the tweet by performing a mod operation, checking for even division. So is at in the text? No, because 7 doesn't divide evenly into 50,065. U, yes. We don't actually do division because you can just do bit shifts, which are a lot faster, but that's the idea. Spatial intersections are performed with rasters. So it will take a shapefile, rasterize it. This is Egyptian administrative districts. It actually works well in the CPU too. So you just take the point, for example, find its appropriate coordinate in the raster and look up, and it's not actually colored like this. Each pixel in the raster is the ID of the corresponding polygon. So you look it up and say, oh, that's polygon 32, that's Minya district in Egypt. It's very fast. One mid-level GPU, $200 GPU can do nearly 1 billion a second, and it scales linearly. This is stuff I couldn't do with PostGIS in my research because I know people can tune it to get maybe 5,000 intersections a second, but if you have a data set of 1 billion tweets or anything else, it's not going to work. So we got about a 700,000 times speed up on that. Rendering heat maps. So it uses CUDA to render heat maps on the GPU. Is this actually a PowerPoint, or is this oops, this is I actually have a video of this. But first, it just plots the points, and then it uses a Gaussian kernel to perform the blur. It does about 20 frames a second, which means that you can have, on our web server, just one computer can serve up, and 100 people can be on there at once making maps, which is pretty cool. I also, since we don't have access to the Twitter Firehose, I built called the Grim TWEEPER. It basically is a big distributed Twitter harvester in the cloud. Basically, the master node can be on EC2 or not, but all the clients or the slaves or the harvesters are in the cloud. Here's 15 right here. You turn them on. Each has a different IP address, so you don't run into Twitter's rate limitations. We're pulling in about 500 a second, which is about 50 million a day on these, just half of the United States. So you could conceivably, we will seek to get all like 300 or 400 million tweets if possible. Then in real time, it uses geo names and a hash table to geocode all the, and puts them right on GEOPS, and they can be displayed immediately. So that's it. Hold on. I am gonna show you. I had a video of everything at work, but it was too big. I do have this. This is my original prototype. It's not the opening? I guess not. It's unfortunate. Oh, okay. This is the mentions of the iPad from January to March 2012, and you can see the spikes at the end where people get excited about the release of it, basically. So if you want to check out the internet connection is really too slow in here to handle the world map site. It's worldmap.harvard.edu/tweetmap. If you want to check it out. It's not been tested that much, so if it crashes, it's not my fault. So, but it will be online full time as soon as we get the server installed that we're working on. Yes?